All right, part two, technical language processing. So part one was the text mining and feature extraction. Here we have technical language processing. Technical language processing is a subset of natural language processing, and it can provide summaries or determine importance of words and phrases. So ignore things like the, a, and give me the meat and potatoes of what the data sheet is actually trying to say. Existing uses are domains with large volumes of data. So materials engineering, there's a research paper that we'll go over that uses technical language processing, medical journals, maintenance journals, records, and the list goes on and on. There's some computer science, essentially any domain where the information is highly technical, so a natural language processor can't fully understand what is and is not important, and with a large text corpus. So a lot of research can be used on a lot of research fields where journals have been published. Here we will go over our first case study. So materials research, the pros to this are a large corpus for training. So materials research, this is material sciences. So finding new materials or finding existing relationships between materials and their characteristics. Problems that they ran into are costly manual information extraction, which we've already discussed. It's very labor intensive. Unstructured formats, they have HTML, PDFs, and some others, XML representations, and the layouts can be different. So tables are located in different places. Some have figures, some don't. Some have different sections, introduction, description, etc. With this tool, they saw a rule-based extraction score of F1 score of 77%, which is pretty good, and they extracted the metadata, which metadata is stored in HTML and XML. PDFs typically don't have metadata. It's data that's hidden behind the document almost, but it's key for feature extraction. So our metadata will be features that we had discussed previously. And then document structure, extraction classification. This is labeling sections like the introduction, abstract, etc., and noticing that those are separate chunks of text. They also have to deal with subscripts and formulas, which you saw in the Zener diodes, that we also have subscripts and sometimes formulas that are difficult to understand if you don't already know what they mean, and that can be time consuming. This is continuing on the previous document, or the previous slide. So logical structure recovery and scholarly articles. This is another example where you can see on the right hand side they have successfully determined what is what's a figure, what's a caption, what's an equation, what's body text, and these can be stored outside of the PDF for easier retrieval from a database because you don't actually have to open the PDF. Now you have a text representation, and it can help with discovery of new material. The goal was to use computers to assist researchers to locate and annotate scholarly articles, similar to what we're trying to do. And they used conditional random fields. Parsit is a tool that they used, which is what you see on the right-hand side over here. Collecting metadata, this is another example. Sermine, this is another paper that discusses a similar problem where they are trying to extract the metadata from journals. So again, title, author, affiliation. These over here on the right show some other tools that you could use to do the same thing. Could this be tailored to domain-specific fields? Possibly. That's room for expansion. Technical language processing and materials research. Their goal was to, again, use computers to improve information discovery with materials research. And they have a lot of similarities with what we were trying to do. So first they marked up the text, processed it, produced a text representation, this bag of words, TF-IDF. This is common in natural language processing, but they had to recreate technical language models because the existing pre-trained models for natural language don't do a very good job with this technical information. Over here on the right-hand side, you can see some examples of what they were trying to extract. So keywords, keywords are dissolved, mixed, dried, calcined, and they have temperatures and times with abbreviations. These are all things that might not be necessarily one-for-one comparison with electrical engineering, but they're in this, they share some similarities. So, technical information, values that are very important. So, for instance, 80 degrees Celsius and 5 hours is a key piece of information, but a natural language processor might not notice that was key. So, and they also have to do table extraction and notice action words, as well as domain-specific nouns. Case study number 2. Maintenance records. So pros here are they have a large document text corpus, and one thing that's interesting in their research was they actually had human-in-the-loop intervention because they realized that it was unlikely that they would get a perfect action generator without a human who understands what those actions mean. So they also have abbreviations and domain-specific jargon, technical verbiage, plugged, replace, troubleshoot, and punctuation that's non-standard and significant. So this is something that is echoed in my research is that those mil specs there's often hyphens or dashes that are extremely important field delimiters where you need to know that first piece is the series number and then everything that trails it is component specific. This is the pipeline that they suggest where they reuse components from standard natural language processing, but you can see on the right hand side they have a domain expert that doesn't have to understand what's going on within the technical language processing and NLP pipelines. They have an analyst that can control these two sections, and what the domain expert gets, or the actual user, is information about what should I do next, so I'll show you an example in a couple slides here of what maintenance records are right here. So maintenance records are maintenance work orders, replace air dryer silencer, pump electrically dead. I don't even know what U/S means, but someone who does this for a living probably does know what that means and needs the model to understand that that's an action. And again, lots of technical writing in here. And what they were trying to do was reduce manual efforts for planning, scheduling, and executing maintenance. So someone puts in a work order or someone performs maintenance, this information gets stored in a database, and that database is it's difficult to discover new information like, oh, the air filter has been replaced once every 3 months for 2 years. Okay, produce an action that says go replace the air filter in 3 months. Case study number 3, component advisor. This is pretty much exactly, they address the exact same issue that I feel in industry in electrical engineering. So I've included a quote here. The web cannot offer answers to queries such as find the flash component on the market with a cycle time no greater than 120 nanoseconds and availability within 2 weeks. This is very similar to the types of Google searches that will not give you an accurate response. You're going to have to go and manually find this information, and it can be very, very time consuming. Not to mention, if that part goes obsolete, you have to do it again. And all the work that you've done previously doesn't really matter because you have to start from scratch again. So what they did was they built a product concept and a document model, and they tried to find overlap between the two. You'll see what this means in future sections. A product concept is what makes that part that part. So for instance, for the diode, what, the Zener voltage and the operating current, all the things that could be controlled for that part, basically create a model where these fields are empty and you can populate them. The document model reads the data sheet and tries to fit the information it pulls from the datasheet into the product concept, and then store that information for future retrieval. On the right-hand side, sorry for the grainy picture, is the product concept model for memory. So this is, you can see non-volatile memory, and then on the left-hand side, this is volatile memory, RAM. These are so flash, base mode, timing. These are all things that I'm sure to these users was very important and are the types of information that are inherent qualities to that product. This is the document model where it's extracting this information from the document and is trying to place this information within that structure that was described in the previous slide. This is the architecture that I propose for text mining and technical language processing, ending with a database search and retrieve. That would be, the market-ready version of this. So first, you have text collection. You can crawl the web, or there's actually APIs that vendors will allow you to do 1,000 calls per day. So you can actually pull 1,000 data sheets down in each day, and so you can pretty quickly generate a text corpus. And there's some neat tools that you can do with that. Next, you have to mine the data. So we discussed text mining, the table mining, and feature extraction. These are two tools that I use. There are countless others. Next, you move on. You take that information and you use that to generate a technical language processing model. TF, IDF, that's term frequency and inverse document frequency. Term frequency is how often does that word appear in the document. Inverse document frequency essentially divides that by the length of the document or the number of documents, depending on how you want to define IDF. And parse it and is one example. TLP weighted rules. This is where, say you have a value that is bolded or is a section header, or those should be weighted more highly than just a standard single occurrence. So if you see something in the document so say something comes out of a table, typically tables contain the very, very crucial information. And so you might want to weight those values as occurring twice when they really only occur once, because they're that significant and can possibly improve the technical language processing. Or the proximity. So we had XY location. Well, if you have two things that are close to each other, those may be more related. So you might want to weight those higher than things that are placed farther apart. Finally, you would take the technical language processing and these features, and you ideally would store that information in the database and then do a search and retrieve. So you could use this information that you've extracted and stored alongside your PDF and find that information more quickly. In conclusion, there is a need for this, as shown in previous studies. The component advisor that I described before was one of two. That one was conducted by researchers at Hewlett-Packard. There was another one done by IBM around 2000. Both of these are closed source research, and there's not much documentation for them, but both of them recognize it's really a pain to dig through these PDFs and try and find this information. For engineers whose, the bottom line is time is money, the primary cost, if the part costs $100 and you spend 3 hours trying to find that part, well, the man hours have now exceeded the cost of the part. So it would be nice if you could find it quicker. Ideally, you could retrain it for specific domains. So produce a tool set and distribute it to people where they can implement it for their particular technical domain. So mine is electrical components, someone else's was materials, someone else's was maintenance records, and perhaps human in the loop intervention would be a first step. People who are domain subject matter experts might be able to help train these models and help label the data and improve them iteratively. Previous methodologies could be expanded given new tools